Today I would like to introduce my another paper of the series, Robust Estimations from Distribution Structures, Non-Asymptotic. Previously, we're mainly focusing on asymptotic bias. If we consider non-asymptotic bias, and there are many obstacles, and because first I would like to briefly overview the development of finite sample bias correction. And the sample variance is probably the first finite sample bias the statistician identified that if you're just replacing the population mean with the sample mean, and then this is population standard deviation. Remove this square root, and this sample variance, however, it is a biased estimator under the finite sample scenario. And so Bessel suggested that dividing this factor to obtaining a unbiased sample variance, and this correction is called Bessel correction. It was introduced in the early of 19th century, and this is. And then taking us, this is the unbiased for any samples provided that the population, for the finite second moment, right? If you're taking a square root of it, obtaining the sample standard deviation. However, this is also a bias estimator. And if you want an unbiased estimation of standard deviation, and there is no formula like this, and you must assuming some very specific assumptions. And here if you're assuming a Gaussian distribution, and then the correction factor is this, and you're just dividing this finite sample by sample standard deviation dividing by this factor. This factor is very low, nearly about 20% relative to 1, and then gradually higher. But if you consider 3 decimal accuracy, it should be reached nearly 1,000, and then nearly 1,000, and then Kramer, if you consider later so nearly 1,000, and then for other higher order central moments, an advantage of central moment is that Kramer later he showed in his classical textbook Mathematical Methods of Statistics. He showed in these very classical textbooks that it is possible even for very higher order, any arbitrary order, it is possible to achieve unbiased sample central moments. And the exact algorithms and algebra for the up to 6, and this was proposed by Jolovina and Haber. It is here, and you can see that although relatively complex, but we can achieve unbiased estimation of central moments, and under a non-parametric assumption. But for other estimators, even just the standard deviation, we need a distributional assumption. And if we consider the robust statistics, the situation is much more complex. For example, just because it is based on order statistics, for example, 1, 3, 5, 7, and in this case, you need to consider, for example, 3 or 5 medium, or you need to, or for the trimming, you need to consider also this second among a sample with 5 sides. Consider the second value, right? And then this distribution is highly depending on first is the order, whether it is first, second, and then it is also depending on the cumulative distribution and the probability density function. And so in this case, for example, this is relatively complex. I would like to show a lecture of Colorado. For example, here is the minimum value is here. The probability density first from largest to this first, of course, the minimum, because it is close to the minimum, so it is very high, and then gradually down, close to 0, and then the maximum, the probability, the density function, it is here. It is this, and then for the maximum values, it is like this. If you consider the joint cumulative distribution of maximum and minimum, this is very useful if you want to compare the sample range, right? And it can also be deduced, although also very complex. And then joint distribution of the order statistics, it is like this. Finally, deduce this formula. If you're interested in this topic, and I recommend you to watch some YouTube videos, and there are some. But generally, the issue of order statistics is that we can write this formula. But even, for example, for the medium, when the n is odd, we can write this formula. It's just because the expected value of the medium under the finite sample cases is just the expected value of this distribution, right? So you just integrate it. But an issue is that although we can write the formula, but we can hardly solve it. I mean, you can already see how complex this is. If using the exponential distribution, this is a very simple cases, right? Just the exponential, and then you plug in this. And then in these cases, it is analytically solvable, although this result is also already very complex. But if for some more complex distribution, for example, the Gaussian distribution, to my knowledge, it is intractable. But maybe someone can solve that, I'm not sure. And if you consider more complex robust estimator, for example, the medium absolute deviation, we can also write the formula for the finite sample distribution. But it is already very complex because we need to divide the odd case and even case, and for even case, you need to consider the n equal to 2 and equal to 4. the n equal to 2 case, if you use the exponential distribution, it might be solvable. But for other cases, I don't think it is tractable even using the exponential distribution. So this is the finite sample correction. This factor was mainly deduced using, it's not deduced, it is mainly obtained using a Monte Carlo simulation. And the first is from the Croux and Rousseau in 1992, and they're using 200,000 pseudo samples, and here 200,000 samples, and obtaining this factor. And then later, Kevin, he used 10 million samples from 2 to 100. And yes, from 2 to 100, as you can see, the behavior is pretty complex. And then after that, a researcher in Huawei, and this is I found in archive that he used 1 billion sample, half billion sample to create this table. It is from 2 to 3,000, as you can see. Even for 100, this, if you're pursuing a 3 decimal accuracy, it is still not enough. If you're pursuing a 3 decimal accuracy, you need to reach nearly 3,000, 2,000. So you don't need to worry about this finite sample bias. And so generally, that means in most real cases, and because most samples is unlikely larger than 2,000 in real, especially in biology, it is unlikely higher than that. And so that means in most cases we need to consider the finite sample bias. And if we pursuing a 3 decimal accuracy, but however, this is first, it is not in most cases not analytically tractable. And although we can use a simulation to estimate the factor, but this simulation, this computation, of course, is very expensive. This 1 billion samples, only some very big companies have such findings, and also some very big groups. And yes, and this is the issue that, and also this is just for the Gaussian distribution. And if you want an exponential distribution, this is not suitable, a very high deviation. And so there is an issue that. Because in real-world scenarios, there are many different estimators, and some estimators might be it itself might be very complex and requiring a lot of computational time. For example, previously we developed the invariant central moments, and it is pretty complex. It requires computing the combinations of more than 300 different combinations, and this more than 300 different combinations, we need to obtain this. So we need to solve that. It is much more complex than this medium absolute deviation, and then second. This is the first, and then second is that if we can and so this is, there are two issues. First is that it is very complex, require a lot of computational time, and if we further consider the computational time of the estimator itself, it is much more complex and expensive, and then also the scenarios are very different. We often need different factors for different distributions, and therefore such things are pretty intractable for ordinary users. And we can only download it. For example, using this finite sample factor, we obtain it for online and use this factor. Maybe although it might be not suitable for our research, but you correct it, it is better than not correcting, right? So and this is one case, and another case is that we don't know how to the complexity of this finite sample, these distributions, and make it, basically we don't, although we can write a formula, but there is no very intuitive understanding on the behavior of such distributions. And so therefore, generally, we can hardly think that, although we can write a formula, but what is the nature of randomness? And because this finite sample distribution, it is indeed, as we said, we use a Monte Carlo simulation. The Monte Carlo simulation, it is essentially like we use first generated using, for example, in the R using run if. It is generating a sequence from 0 to 1, right? From 0 to 1, and then 0.1, 0.113, or 0.18. Anyway, 0.9. Anyway, it is generating a random sequence, and then we converted this sequence into the distribution we wanted using the quantile function, for example, plus quantile q 0.1, using this quantile function, and then this we can generate it, for example, the finite sample distribution of the, for example, if we say the quantile function is the Gaussian distribution, and then we can obtain a value, right? And then the issue is that, of course, we yes, and then because so that means all our this finite sample is indeed essentially related to the randomness of this uniform distribution. So uniform, because this is a uniform distribution. It is a, for example, this is the this is x-axis and y-axis. The uniform distribution is here. It is like this, a uniform flat distribution from 0 to 1. It is a flat. So all these finite sample behaviors, it is essentially related to the randomness of this uniform distribution. And this uniform distribution, it is the nature of all Monte Carlo studies, because all Monte Carlo studies are essentially generating random numbers from 0 to 1. And therefore, we want to know the nature of randomness. If you further consider that, if we know the nature of randomness, so maybe we can solve this issue to obtaining a better solution, right? And now I tried an approach that first we need to, for example, we simulated this histogram. We first simulated this, and then you can see that this distribution, it is essentially like this, right? And then if we again simulated another one, like this, or we can again, yes. So these two are very similar, right? It is like this, right? So that means, although we anyway you can plot the histogram, so it is another distribution like this. So you can, so generally, although this is a uniform distribution asymptotically, but each time we run that, it is the sample. It looks like a very different distribution. For example, now it is like a unimodal distribution, right? So it looks like a very different distribution. So we consider that whether it is possible, we decompose it, this uniform, the random, this finite sample behaviors, the randomness of this uniform distribution, into several different distributions. It is just like Fourier transformation. We decompose it into different transcendental functions. And so in these cases, we try. For example, now this is my first approach, and here, for example, here now, first we consider a arithmetic sequence. Yes, yes, arithmetic sequence, it is a uniform distribution, right? Arithmetic sequence is just this sequence, 1, 1, 1, 1, 1, equal interval. So it is a arithmetic sequence. And then it is the beta distribution. So this is probably the first most natural approach we approximate uniform distribution, right? Because it itself, it is uniform. And then we consider the beta distribution. Beta distribution is like here, it has an interval from 0 to 1 and 2 parameter controlling the shape. So it can be unimodal or even 2-modal, and left square and right square, or even monotonic. So it is a very desired distribution that we can, if we try to approximate the shape of this the asymptotic behavior, the beta distribution is a very natural approach, first guess using the beta distribution. And first we consider if we adjusting the shape, this shape, as adjusting this shape. That's okay. And then it is a U shape. And then it is this is a U shape. This is an N shape. Okay. And then this yes, and then we consider another shape, N shape. But this is with left scoot. You need to know that it's 0.2 and 0.4, and there is 0, so it is a left scoot. It is 0, no values over 0.4. And then we consider the right scoot. Right scoot. Oh wait, this is not right scoot. This is left scoot. Wrong. This is left scoot. And then we consider another case, the beta distribution mixed with arithmetic sequence. Yes, and this is the arithmetic sequence, and then the mix with a beta distribution like this shape. And then beta distribution like this shape. And then beta distribution, we further consider a right scoot cases, but this time it is monotonic decreasing. And then we consider left scoot cases. Okay, left scoot cases, okay. And then if we mix the left scoot and right scoot cases further here, okay. Yes. Okay. And then also the mixed, so it will be a shape like this. And then finally we consider a random sequence. And this is the reason I will explain a little bit later. So generally, the principle is like that. We try to decompose it. The sequence, for example, this is, for example, for the general uniform distribution. It is maybe I can call it U. We want to decompose it U into x1 plus x2 plus x3 plus x4 different shapes, right? And blah 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 x maybe 10. Okay, and then plus a random sequence. This is because maybe the above it cannot fully approximate, so we want to add it a random as an error correction. So this is and then we are assigning a weight in front of each sequence. For example, maybe 0.8, any weight, and then our approach is that because we can obtaining because the bias, finite sample bias of central moments is obtainable. So we first, for example, use the Gaussian distribution. We use this sequence. They obtained this random sequence, plugging into the quantile function of the Gaussian distribution, and then we are obtaining this sequence. We computing the first 4 moments of this sequence. I just assuming, for example, for simplicity, I just consider the variance, okay? And then, for example, if I say that the variance of this first, it is maybe 0. I would just say this is also x1, okay? And then x2, x3. Anyway, this x1, x2, x3, x10, it is equal to the variance. We can just assuming that these are all equal to, we use the computing the sample variance, biased sample variance without Bessel correction, without the bias correction. And then we can expect it that because here we use many different sequences, and then if we are assigning a weight in front of it, if we assuming if our expectation is correct, the uniform distribution can be decomposed into such 10 or 11 or 12 sequences, different sequences, and then we obtain assigning a factor in front of each sequences, and then we we're assigning a factor in front of all this sample variance without Bessel correction, and then this will equal to what? It will equal to the biased variance, and we can expect it biased variance, and this is just for example, we 1 over n minus 1, right? So this is just it is just like that. We're just multiplying this factor because we just know the times the population variance. Yes. So no. This is n it is high. No. It should be lower. Right. Yes. It is. So that means this will be equal because our estimation it is biased. So it should be also biased, right? So we can, because we know this correction factor, so we can computing the expected bias variance because we know. So we know this factor, and that means this factor was already even for higher central moment was already deduced. We're using this Jolovina and Haber's algorithm, and using this we can say that this uniform distribution we can computing it, and yes, and then this equation we can use here we can solve this equation here, right? Yes, here is an. This is we randomly guess it because because indeed we this if you just solve this single equation, of course it is there are many solutions, but we can obtain many different. There can be many different because not just variance. For example, the second can be the third moment, right? And then fourth moment. And then also this is the Gaussian distribution. I can also consider the exponential distribution, right? So generally there are many after we forming many different equations, and then we can try to solve. And I use we can try to solve that. Optimizing, we can try to optimizing it using an optimizing algorithm. And then this obtained result is like this. Yes, the obtained result is this. Yes, it is like this. You can see for this sample size. This is 19. Okay. For the first weight, it is 0. It is about. You still remember that the first weight it is about we using this. The first weight we're using the arithmetic sequence, right? So you can see that the first arithmetic sequence takes about normally it takes about 50% or even higher, or even sometimes 70%, right? So that means this arithmetic sequence, although you cannot completely explain, but it can explain about 50%, half percent. So that means the randomness of the uniform distribution, and when we just consider when it is about 16, this randomness is about yes. When we consider 16, and then this randomness is about just 50%. And if we consider, for example, the sample size, if it is going to 1,000, even 2,000, And then this, of course, this arithmetic sequence will it takes account much higher, right? It will take us about more than 70 or 80. And then another the second, for example, that it is better U-shape, and then it takes about 20%. And then for others, it is much lower. And then yes, as you can see, it is much lower. So the yes, much lower in for other. So mainly this and you also you need to remember that the last one is the random sequence, but in most cases, this random sequence, the weight is very low. So that means we're just using the above this about 10, 11 sequences. It is enough to takes account for most of the randomness of this uniform distribution. And that, so this reveals a very interesting result that first we need to show that that the weight of the randomness of the arithmetic sequence, it gradually increasing. I haven't taken a simulation. I previously took a simulation, but now I haven't took that. You can take that by yourself, and there. You can take that by yourself, and I post the algorithm in GitHub. And generally, by the arithmetic sequence initially, when the sample size is 16, initially it is about 50%. Then it gradually going to 100, nearly 100 when the sample size got infinitely large. So this is the first case, and then the second case is, and then this is, so we just consider the weight. It is like that, and then we consider the this is the weight, and then we this is the weight of the arithmetic sequence, and then beta U-shape. Beta U-shape initially 20%, and then it gradually down. It is like that. Anyway, that other ways gradually down. The arithmetic sequence gradually grow. The basic trend is like that, and for and there are some sequences have higher weights than another. And if you're interested, you can run this and comparing it. I haven't drawn a very nice graph now, and this shows that the randomness, we can decompose it into several sequences, and then because after we decompose it into several sequences, so it is possible we can now we just run these sequences. We're just using these ways to run these sequences, using these sequences, estimating other estimated. For example, we can estimating the standard deviation. It is bias, right, or the mean, and then we can obtaining. You can see that this obtaining the arrows is pretty small. The arrow is very small. Yes, and this so that means we just have for about 40 samples, and we can very accurately estimate the finite sample bias of medium and standard deviation, and even for more complex estimators. And I will later show that also in GitHub you can watch that it can reach a very high accuracy just with about 40 samples. And this computational time computing to 100 sample, 1 billion sample, it is not the same level here.